Okay, good morning, everybody. Um, so today we will continue working on the exploratory data analysis, and I will show how to create the pipeline that will clean your data, and you will be able to apply just in one line this pipeline to your raw data and get nicely looking metrics with now numbers. Okay, so this is we don't have problem solving. I will just go through my notebook, um, lecture 4, and if you want, you're welcome to follow me with running the code. So last time we worked with this Titanic data set, and we decided that we will drop some missing values from this column sex and embarked. There were 5 and 2 records. And as I mentioned in the end of the class, we didn't split into train and test our data set. So now we will start with target isolation and also splitting the data into train and test, because we don't want to use any information from the test part. We don't want to use information about age. We don't want to use information about some classes that we can see in the test part. And then we can run into a problem. Think about the situation when we have classes like the port of embarking S, Q, and C, and somehow we split our data set, and in our train part, we have only 2 classes. It can happen, like just C and S, but we don't have class Q in our train. So how to deal with this situation? It's possible that we split our data and we will see a little bit different data in the remaining part, different classes. So if we apply one code encoder to our original, to the first part, then we will get actually an error when we will try to apply this one code encoder to the second part. So this is one of the problems, and in this function train test split, by default there is parameter what's called stratify, and by default it's true. So if you look at the description, there is parameter shuffle, also by default it's true. So when it creates this X test and X train, it also shuffles the rows. But also there is parameter stratify. And by default it's none. And if it's none, it will split your data to keep the proportion of classes of your target of Y. So to get the same number of survived, not survived in the train part and in the test part. Because it's also possible that you will split your data, and in your train part, you will have only survived people. So Stratify takes care of the balance of the classes to keep the proportion of over all data set to each part. But if you want to keep also the proportions for other features, you can indicate these tables in this stratify variable. As like, let's see, there is example. Well, so here you can just pass the column names and then it will split your data, also taking care to keep all the classes in both train and test parts. Okay, but what if we will get a new data, like from a user input, for example, and in this data we will see a different class? Then you will deal with this in the next homework. Actually, on week 4, not week 3. One-hot encoder also has parameters. When we will apply one-hot encoder, I will show you the parameters. Okay, so this is first steps to split our data for now in 2 parts. Later we will split into 3 parts: train, validation, and test. The first thing, as you remember, we wanted to apply, we wanted to drop some columns. And we did this column by column. Now we can do this in one line. So we can import this column transformer from scikit-learn and pass some parameters. In this case, I want to draw columns and list the columns that I want to drop. In this case, passenger ID, name, and ticket number. And after that, if I apply transform to my data, train data, actually, you won't see the passenger ID or passenger name anymore because it was removed. Unfortunately, it returns an NumPy array, so it doesn't return the column names like data frame. If you want to keep the nice looking table, this transform one column transformer has parameter get feature names out. So it will return the list of the remaining feature names. So these are remaining feature names. Oh, by the way, remainder. What does it mean? It's important. In column transformer, it will return only the listed columns. But in this case, we drop columns, so it will return nothing without this remainder. So this parameter remainder pass through keeps all unlisted columns unchanged. So every time you should use remainder pass through if you want to keep other columns. Okay, so after that, that's why other columns they have this prefix remainder because these are columns not listed in our transform. After that, we can create a data frame from the transformed NumPy array matrix and use as column names this column names that returns our column transformer. And then we will get a nice looking table with column names. Okay, so this is the first transform. We removed 3 columns, but we could remove 3 columns also in one line with pandas. Now we want to convert nominal features in one-hot encoder. And now we will create another transform one-hot encoder, drop first as usual, and create another pipeline where we will apply two transforms and removing columns and applying one-hot encoder. So I apply one-hot encoder that I initialized earlier to this listed columns, text and the bar. And then I apply also drop columns to these columns pass through. And as a result, let's print this with column names. We get a matrix, and instead of column 6, we have column from one-hot encoder, which corresponds in this case to class male, and 2 columns for embarked, which without the first column. And now we have pretty good table. Now we should take care of nonce in the H column. And I will create the third pipeline. I import simple imputer. And here we can use, for example, median instead of default mean. And I create the third transformation pipeline with where I apply one-hot encoder, imputer for column H, and drop columns. It doesn't understand median. Let's see. Strategy mean. What are the strategies? So how to open help shift H? No.
It was just a typo. Spelled MEDIAN.
Oh, thank you.
It's IA.
I. Oh, thank you. Yeah, now it works. So, and here we have this transformer. You can see which columns went unchanged, which columns were dropped, which columns were imputed, and which columns were we applied one-hot encoder. And we get features out and cast into data frame again to get a nicely looking table. And voila, the entire class that we spent last time just in one line. And so we apply transform to our raw data, X-train, and as the result, we get the nicely looking table with numbers. And we can apply any algorithm for scikit-learn, even without understanding how it works, and we will get some prediction. So, okay. Now we will go. Um, oh, I promised to tell you how to deal with missing values with missing classes in one-hot encoder. So in one-hot encoder, there is parameter handle unknown, handle unknown, and by default, handle unknown returns an error. So if you have like new data, and in this new data, you will have missing values or a new class label, then your model will return an error. But you can use other strategies. Um, handle unknown. So other strategies are ignore. So if you will get like missing value, it will just ignore it. Infrequent if exist. So this strategy actually will create a new column. A new column with label with this label, but it's the same as unknown. So every um, every class, new class that we didn't see in our train set will get one in this additional column. But you will use this when we'll talk about classification, and it's on week 4. Okay. And now we will create pipeline not only for cleaning data, but also for applying our model. So let's import classifier k-nearest neighbors. Here we can just apply this. We can create transformed data. And as you remember, it returns NumPy array. So X-train transformed will be a NumPy array. And we can apply our classifier to this matrix. Calculate the predictions. Predictions will... Oh, by the way, I didn't mention that in scikit-learn, you can, for labels, you can use nominal data. For example, if you had there survived, not survived, it would work without problems. And predictions would return also the class survived or not survived. So for labels, you don't need to cast them into numbers if it's classes, for example. So and again, it's a good idea to use just built-in accuracy score. Oh, sorry. Oh, neighbors score. And it's the same as to import the score function from scikit-learn and to get this. Okay, but now we will move forward and we will create a so-called pipeline. So we import pipeline from scikit-learn, where we apply both and transform and model. So here is our pipeline. The first level is our data preparation. The second level is the model that will be applied. And now we can get the predictions from our raw data. You remember, X-test is uncleaned data with names, with missed values. But we will get the predictions on this data immediately using this pipeline. And then we calculate the accuracy. So I think it's very, very elegant way to work with raw data. Okay, so last time we didn't actually analyze one feature. We didn't analyze the column pair. And let's look at this column now. So I plot the distribution. So that's it about pipelines. Now we will talk about data preparation in more details. We will talk about bin horizon now, splitting into bins. Okay, so this is the distribution of the column fair. What can you tell me or understand from this distribution about this feature? Does it look reasonable? Yep.
It's very skewed. Go ahead.
Yes, and do you think I'm not sure if this number is correct? Of course, maybe one person was ready to pay any amount just to get on the Titanic, but maybe just misprint. Yep.
I was just wondering a bit about the difference between the curve and like those 3 points of data, specifically the one that goes up above 200, the one that's like around 75, and the other one that's like around like 62.5. Just that all of the ones that are above the curve.
Oh, which these two columns?
Yeah, I just thought it was kind of interesting. This
It means that as you remember, when we imputed age, we had this peak for average. So this means that just for the majority of passengers, the ticket cost was in this range. I don't know what are these numbers. It depends on what is the width of the bin. Okay, so let's see. First, let's print the correlation. So I add to my data the target. I add the target because in correlation, I want to see the correlation between every feature and target. And where is age? So age. Oh, sorry, we're looking to fair. The column fair has correlation 0.019 with column survived. So very, very weak correlation. this is another way how to look at the feature importance. You can look at the correlation between the column, the feature and the target. So for example, looks like the largest correlation is with this port of embarking. Negative correlation. So yes, if you have siblings, then it will actually drop your um, uh, um, ability to survive. So okay, if we have this very noisy distribution for the feature, the common way to make it more informative to split into chunks. So let's say we split this into three parts, like this part, then this part, and then this part. So in this case, all the outliers, and actually we don't know if there are outliers or maybe these are just unique passengers with golden toilet, I don't know, room. So they will fall all in one grid. So let's do that. In pandas, you can create beans indicating the range manually, like the first line. Oh. Or you can use just the number of splits, in this case 5, and then it will split uniformly into bins. What? Um, Oh, actually, in this case, I apply this to H. But what is the error? I understand. So if I indicate my own bins, it works. If I using the int edge must be unique. Ah, the duplicate. Hmm, interesting. If I'm using less number of bins, okay, then it works. Okay, so in this case, it splits my age into ranges. And then you can apply ordinal encoder, and ordinal encoder will convert these ranges into numbers 1, 2, 3, 4. And this will be a new feature for age instead of like 25.5 years, 25.7 years, because there is very small difference. We can combine this into one group, the people in this range of age. Okay, so, and there is also built-in method, k-bin discretizer, that will create a split your data into k-bins. And also there is parameter encode. It will automatically encode these intervals into integers, just the first bin, second, and so on. So, okay, I create the next transform 4, and also add this. Okay, here it's without binarizer. Let's look at the heat map, age, and the correlation is this one, negative 0.14. Oh, wait a second. It's with binarizer. It looks I missed something. Oh yes, because I created transform for H and I'm using transform for H with binarizer. Let's look at the correlation without binarization. H with our target, the correlation was smaller, 0.05. So you can see that binarization actually helps to make this feature more informative. So the main idea is that we reduce the noise in our data. If there were some mistakes, somebody just maybe edit, or women at that time, my grandmother actually also did the same. They preferred to lie and tell their age smaller. So my grandmother changed this in passport, and she was smaller. She was younger by 1 year. But at that time, nobody could check actually the real age. But when we binarize, we group these people, and these errors actually will be reduced when we look just at the groups of people. Okay, so this is about binarization. The other thing that I want to mention is, so this is so-called a Pearson correlation, but there is also Spearman correlation. I want to go, okay, I actually can do it here. So here I plot this correlation. And by default, it's the standard correlation, which is called Pearson. And the formula for correlation is this one. Just we subtract the average from every point in one column. We subtract the average from the target and divide by the standard deviations. So this is called Pearson correlation. But there is also Spearman correlation. So you can use parameter method, I believe. Or maybe with A. So let's look at some numbers here. For example, age now is changed. It was 14, now it's 11. But the other numbers, they should improve typically. So for example, fair 0.15? What about x 0.32? And without this, well, it's pretty the same. Well, typically Spearman correlation would give you a little bit larger numbers for correlation. But in this case, it's the first column is the same. I believe the second column is changed. So the second column now is 0.66, and if we use Spearman, oh, it's still 0.66. Okay. Weird. But typically, yes, typically it should change a little bit because do you know the difference between Pearson and Spearman correlation? So Spearman correlation is so-called rank correlation. So if you have some data like this, we sort our first column. And instead of numbers in this column, we are using the ranks. So for just natural numbers. These numbers correspond to the first column. Then we sort the target column. And what is the smallest number? 2. It will get its rank 1. The next is 6. It will get rank 2. So instead of taking correlation between real data, we take correlation between the ranks of this data, and it's called Spearman correlation. And do you remember which dependency actually between data the correlation reflects? Only linear dependency. If our dependency is non-linear, then the correlation coefficient will be small. But our features like age, most likely they're not, there is no linear dependency between feature and target, because I believe for small h and for large h, it's pretty the same ability to survive than for the middle age. So it will be kind of parabola instead of linear. And correlation will be pretty low. And actually, you saw that it was 0.014, but it doesn't mean that this feature is not important. It's just because correlation doesn't show this dependence. So another measure of dependency is called mutual information. And the mutual information, so Spearman correlation also takes a little bit care of this nonlinear dependency. And mutual information coefficient, it actually will show the nonlinear dependencies. So let's move to the next parameter that we can check. Let's see what I'm doing here. Oh, before we're moving to the mutual information, I created a new transform where I binarize the fair. Where I binarize the fair, so apply this transform. create pipeline and look at the accuracy. If you compare this accuracy with our first model without any transforms, it was 0.67. And with binarization, it's improved. So, okay, I have scaling data, but I don't see mutual information. Okay, so there is also mutual information coefficient. Um, see. And the mutual information, there are two. One is for classifier, another is for regression. So one is for discrete data, another for continuous data, like age. Uh, in our case, the target is discrete. It's just 1, 0, survived, not survived. And it's in feature selection. Okay. So we can calculate this mutual information for example, between, let's see, I'm not sure if it will work because it's multi-column. Oh, it actually works. Oh, great. So we get this coefficient for all columns in our X-train. And we can look at this coefficient and see which is most informative. It looks like the first one. And the first one, oh, it's the sex. And do you remember uh, which sex was had a higher survivalness when we plotted last time the distribution for column sex? Female was, yeah, female was much higher than male. So this mutual information coefficient has formula bless you, has the following formula. In probability, there is the distance. We talked about distance between points. In probability, there is a distance between distributions, and it's there are different metrics, but the most popular is Kullback-Leibler divergence. So mutual information is defined as the distance in terms of distributions between joint distribution and the product of individual distributions. Do you remember when they actually are the same, when the joint distribution equals to the product of one-dimensional distribution? When these features are independent. If we have independent random variables, then joint distribution equals to the product of distributions. So you can think about this mutual information that it will be zero only if the features are independent completely. There is no dependency. And it will be large if the joint distribution is different from the product of individual distributions. Okay, so great. And the last transform for today, scaling. Also, you will apply this every time. And in scikit-learn, there are two, maybe three, but there are two main scaling transforms. One is called min-max scaling, another is called standard scaling. First of all, why do we want actually to scale our data? Let's look at our data. So we have age, we have passenger class, and what if we want to apply k nearest neighbors? We calculate the distance. The distance. What will be the maximal distance for this call for class? What will be the maximal possible? The smallest will be 0 if they coincide. What will be the maximal? 2 between 3 and 1. Yes. What will be the maximal difference in age? I don't know exactly, but about 100. And you remember, then we sum up these different distances in our distance between points is the sum of distances, absolute values differences between each feature. We will sum up these distances. So, and you can understand that the weight of this feature will be negligible in comparison with age feature. So unconsciously, we introduce the weights to our model. So we don't want to do that. We want to treat these features equally important. And that's why we will normalize features and make them in the same range, between 0 and 1, for example. So this min-max scalar actually serves for this purpose. We calculate the range of our feature, then we subtract the minimal value. So it means that the minimal value will be 0 and divide by the range. So what will be the maximal value after this transform? So the minimal will be 0 because we subtract min from x, and it doesn't matter where we had our point x, it will be shifted to the origin. I will draw this. So let's say we had some numbers. When we subtract the minimal value, then the x tilde will be at the origin. and every number will be shifted by this x mean. But what will be the maximum value after this division? 1, yes, because this is the range. So the furthest point, so this, for example, was x max. After shifting, it will be, I don't know, somewhere here. And this will be actually x max minus x mean, and we divide by x max minus x mean. So after this transform, we will get numbers in the range 0, 1. And also, because it's linear transform, it will preserve the spacings between x's. The second transform is standard, and it's default when you call standard scalar. So this transform is a little bit different. We subtract the mean and divide by standard deviation. So the first question, what will be the range of these transformed variables? Can we get negative numbers? Yes, we can. Because if our points were, for example, in this range from 0 to some number, if we subtract mean, the 0 will be shifted to the left. So in this case, the majority of points will be shifted into the origin. So it can be arbitrary number, but still they will be scaled by standard deviation. It means that the maximal density of these points will be centered at the origin. So still we will normalize our data to the same range. Okay. So, and here I apply standard scalar. And let's look at the accuracy. So now accuracy is 0.76. And if we look at the accuracy before scaling, it was smaller. It was 0.72. Okay, finally, we can plot the so-called pairwise plot. It will take some time. I just want to show this function in scikit-learn. It's a nice maybe starting point to visualize the distributions of your data for all columns, for all features, and so on the diagonal, you will see the bar plots, but they use histograms, so that's why they smooth. For the features, just the feature distribution. For example, age 4, survived and not survived people distribution. In these off-diagonal cells, you will see the distribution between two features. Like here is sex and port of embarking. Yeah, so this will give you some idea about the distribution of your features. Okay, so we're almost done for today. I just want to mention to introduce finally the split into train, validation, and test, because you will need this for Homework too. I will scroll all the way up. When we created the split into train, validation, and test here. So the typical pipeline is when we split our data into three parts: train, then sometimes it's called development set or validation set. So you will see dev or val validation part and test part. So why do we need this validation set? Do you remember in this in homework 1 you had to choose the best K. The best K, the hyperparameter of the model, K nearest neighbors. And as you remember, hyperparameters are the parameters that we just choose by hand. And you used test data in the first homework, but beginning from this week, we will do everything correctly. We will use development set or validation set to tune hyperparameters. So we will use this part for fitting our model and this part for validation. So we will choose the parameter K to get higher accuracy on this part. After we choose this parameter K, which delivers the best performance on this part, we will report the final accuracy or the final metric of our model, and this final accuracy we will report on the data that we never have seen during all our process of tuning our model on this test. Does it make sense? So typically when people report the evaluate their model, evaluation of the model, they report the information on the data that they never used for choosing the model or hyperparameters. So typical split is For example, 70%, 15, or 60%, 20. It depends on the data. When we will work with neural networks and we will use a lot of data, like thousands, then you can use as validation set just 1%. It depends on the amount of data. But if you have 100 points or like 100 passengers and use 1%, then you will validate on one person. It's not representative. And yeah, let's split now into. So you can split, for example, into train test, but after that, you can split your test, for example, into halves. So you can do X validation, Y validation, um, then X test, Y test, and apply again this split. But we apply the split now into the smaller part, which is test. And we will split, for example, by half. So what we have done here, first we split it into 70 and 30%. And then the part with 30% was split into halves. So now we have 15% for validation and for test. And because I didn't change my train, I will just scroll down and and when I report and when I want to look at the performance of my model, I will look at this on validation set. Um, so instead of test, I will use validation. Hmm. Something, what's wrong? Oh, that looks correct. Okay. So let's see. We created this pipeline feed. Why it doesn't work? Let's see. So it works on the test. Oh no, it doesn't work on the test. X doesn't contain any. Okay, maybe I should run this again. X what one doesn't contain any features. It's weird. Oh, okay. I made I messed it up. So I typed XY. I should type X val X train then Y val because now my X test contains actually the target. So here in split, I should change the order. X val X test, Y val Y test, and I should rerun this first line and this line. Okay, and now it will be okay. So okay, so for example, here pipeline. Okay, so I fit my model on train, but I report I don't not report. I'm looking at the accuracy on validation set instead of the test set. Then I apply binarization. Then I look at the accuracy after applying this new transform again on validation set. Or I can choose different K. So every time I will compare performance only on validation part. And I will choose the best model based on the accuracy on this validation part. So here was binarization. Type 2. And I look at the performance on the validation set. Is better. So I will prefer this model. Then I will try another model when I applied scaling, type 3 with scaling. And again, I see that this score is better. And finally, I will report the model performance. Hmm. Validation. Okay, I think it's the last line of the code for today. So I choose the last pipeline because it had the higher score on validation set, pipe 3. And finally, I report this accuracy on the the part that we never used, the X test. So, and you can see that even though on the validation part, the score was 0.79, on the test part, it's lower. Just because there are different data. But this is the way how we actually train the model, because we want to use our model for unseen data in future. Yeah. And it's interesting, just if I try another pipeline, oh, you can see for another pipeline on test data the score is much lower. So our solution was, yeah, there was a question.
I was wondering, how do you determine how to make sure that your model is not overfitting the data?
Oh, so um, so the question is, so overfitting means that we predict nicely on the data in hand and very poorly on the new data. It's called overfitting. So we kind of memorize our data. So partially the using of this validation set, it's kind of our unseen data during training, so we can validate our model on overfitting on the validation set. So k-nearest neighbors is a very simple model. So when we will talk about other models, typically the accuracy in k-nearest neighbors, accuracy, remember, begins from 100% and then drops. But typically for all other models, accuracy begins from 0 and then it grows up. So it will try to predict the training data better and better, and we will need to stop our training at some point, because if we will continue training, then it will perform maybe 100% accuracy on the training data, but on the new data, the accuracy will be very low. So it's called early stopping, but we will talk about this when we will talk about linear regression next week. Okay, and now you're ready for homework 2. And yeah, have a nice rest of your day. We will stop here.